Give me a little example of like what a trait is so that I can like focus my head.
Sorry?
It was a little abstract, like what the traits were. So I was thinking you could help me a little bit, just keep in my head, just like what physically should I be thinking about as a trait?
Okay, okay. Could you explain what
is a trait?
Oh, what's mean a trait?
Can I think about my color or like
Okay, okay, okay. Can I? Yeah. Yes, I will explain with this data set. Yes. When we say a trait, maybe we take body mass here. It's just when there is an evolution, there is a species here, and there are evolutionary forces. Could be mutation, could be drift, could be selection.
And trait is going to be measured continuously? Like
it's continuous, yeah, yes.
Like a trait that's discrete doesn't.
No, it's a continuous, yeah. It could be height. Maybe this can make sense more. Like it could be also any viral disease or something. It may specialize into different species. And we are looking over time how it is changing.
Yeah, yeah, I got it.
All right.
Thank you.
Okay, thank you so much.
Five minutes. Okay. So about Tavakoli, and so let's look at the topic. Mark the server 2 with unbounded buttons.
The good news is that I am the last speaker. So after my talk, you are free to go home after a long day, right? Okay, so what I try to say today is something which is, I'm not sure how close is to earlier talk with by Mark about block matrices, a different approach that I'm going to talk. We are just talking about queuing system and multi-server queuing system. We have in literature, we have one unbounded, which we call it level, and finite or bounded phases. What we try to see if there is any algorithm or any recipe for having two or more unbounded variables. We have to go back to history, how we deal with a spatial case, and then we can, if we can extend that extension, extend that spatial cases to this case. So I would like to introduce something that all of you know, but I just repeat. The reason for having two or more random variable unbounded is because in queuing system, sometimes you need infinitely many or unbounded power or the between queues or servers. So like MMC, GIMC, or MG1 that Mark mentioned before in his talk. So for this reason, we need to study those queuing system that requires more, not only one variable, but more than one variable, infinite. But we study only two random variable in this talk. So we go back to the history of MOM, like Matrix-Analytic method, that you actually, to be clear, we use extrapolating crowd method. I call it ECM. This is basically based on elimination, Gaussian elimination or something like that. And we use iterative method for that. And it seems that is more faster than traditional MOM-based. So we use that in simple case. So our matrix, transition matrix is block matrices, but is, we call it repeated block matrices. So we have lower level G, upper level H on the main diagonal, down and up. And we require to find equilibrium probabilities, pi, which is a vector consisted of vectors of infinite coordinates. This is what we want to find. So the block matrices are between minus G up to H, and everything else are zero, we assume, and G and H could be any integer, but the more integer is more complicated. The bigger integer, more complicated. So we start with understanding how we use ECM to spatial case, which is a scalar case, we call it. So in this case, we have probability, transition probability from I to J, and we assume that the difference between J and I is between minus G and H. And we assume the transition matrix repeats rows from certain boundary. Well, make it easier, assume there is no boundary. All is repeat. So application of that, as you know, is MDC, GIMC, and bulk queues, and waiting time for GIG1. These are application of them. Now, more efficiency, we also compare with the other methods, and then we go to discrete time Markov chain, assume that you have Pij like that, and the M, the superscript M, represent the coefficient of the backward termination. So you cancellation of pi n up to pi n plus 1, and Pijn is the coefficient of the n after n plus 1 cancellation, and this is the recipe for the n plus 1. So n plus 1 is going to be the previous one, like that, and we assume that the last one is Pij, starting with Pij. So we eliminate backward. Now, in order to solve our equilibrium solution, we need two related sequences. This is the main part of ECM. We have to create two sequences related to each other. This is well known. This is not new. This is well known. And this is how we define sequences. We call it AIK, one sequence, and BKJ. Another sequences are related to each other, as you see from these two formula. And then to make it much easier and understandable mathematically, we change the index, two indices into one index, lower index, and superscript index like K. And eventually, after that, by repeating this iteration, we have a convergence. This is the main point. The converge, the first to AI and the second sequence to Pj. So we ended with two basic sequence AI and Bj. So this is the main part of the solution. So we have AI in terms of Pi defined before, and the next AI and Bj, and also Bj in terms of AI and Bj. So basically, you have two sequences, AI and Bj, and you can, if you have AI, then you have Bj, and if you have Bj, you have AI. So back and forth, you find all of these. An algorithm, if you want, you have initial, so you can start with initial 0, and then get B1 and move on. Now, this was a scalar case. Now we go to the block case, but with finite size. So this is, as most of you discuss in this today, I guess, is that block matrices, and but here we have a spatial block matrices that bound around the main diagonal and repeat. Row repeats, as you see. This is the block matrix. Well, maybe you say this is very spatial, but let's just start with a spatial, right? Or example. but we assume that all blocks are have the same size except the P00, but without, well, I shouldn't say without loss of generality, but for today, we assume also the first row also the same as the second row. Make it much easier to calculate all of these. The objective is to find pi I for all I, where x1 is I, and then we end up with pi, which is the collection of all pi as a vector, and x2 is j. And x2 is finite now for this my case. Example, everybody knows QBD, a tandem Q, and with finite buffer. Although other QBD, if you like, is PHC, discrete time GI-G1, any process that X1 changes at most 1. This is QBD. For GIM1, we mentioned Newton's name. X1 is increased by 1, and in this case, H is 1. But decreased by any number. Assuming decreased by G. For numerical purpose, you can consider M as pH, and you have C servers, and you use embedded arrival points in this case. And also, if you look at embedded at departure time, so you look at MG1 and PHG1, for example, in particular PHG1, and in general GIG1, both G and H are arbitrary in this case. It depends on your application. Any GIG1 with finite HG can convert to a QBD. So actually, this is for mathematician. This is not very surprised, because every complicated problem, you try to make it into simple problem. So what I mean by that, I mean that without loss of generality, or you close your eyes and pretend that you are dealing with QBD. Now, still I am in finite size of matrices, and the goal is to find pi i's. So the first thing is pi 0, initial. And then you get pi j, the second formula. I guess I can use these, right? I don't know how to use that, but it's okay, no problem. And number 2 for j less than h, and number 3 for j bigger than h. And if you calculate, if you denote Pij by Pj minus I for I bigger than j, so you have a new notation, is exactly copy of a scalar case. But instead of lowercase a, you have capital A for matrices, for block matrices. So you have Aij, Aj minus I, and Bj minus I. You define these block version of quotes for ECM. And then again, repeat the scalar case. You don't miss anything by repeating for block matrices. You define n minus I to be, yeah, I guess I know that. No, I'm sorry. Yeah. So you have that. You change the index, two index into one index, that's superscript n, and then you use iteration like that. And exactly the same that we had for lower cases, for scalar, not really very much. And then assume for certain that AIN as a sequence has a conversion, and BJN also converge to BJ. So you are ending with two sequences of matrices, finite matrices, finite dimensional matrices. And you get PK, AI, N, and B, IJ, or J, I guess this is PJ, and in a matrix of size 4GH. So this is also numerical purpose, how you can deal with complexity calculation. And you stop iteration as long as you get some successive iteration less than some point or some limit or number. And you can use the same algorithm for this iteration as you use for a scalar case. So basically, matrix case or block case is copy of a scalar case, but you are dealing with matrices finite dimensional. You can also use GTH method. And as soon as you get these sequences of matrices, and then you get the problem solution for equilibrium probabilities. Now, one example I have here is that if you assume H is 2 and G is 3, then AK and BK are known. The initial 6 rows and 5 columns are given like that. Then you calculate A0I and P replace by P0J, and then you end up A01 and A02 for the first row. And move on. And then you get B0, 0 first, and then I0, all of them. And you have initial, pi 0, as soon as you get B0, 0. Up to a factor, right? And then you get others. According to this formula, now, this is done with finite size. So, example, tandem Q with finite buffer. Or shorter Q. I'm going to explain that in a moment. Now, here we have both X1 and X2 unbounded. and blocks are infinite size. How we can do that? Well, there is no equation for pi 0. The sum, we have a condition that the sum of probabilities are 1. This is the first equation that we have, this simple equation. But we have infinite number of pi j. Now, truncating process, you end up with error if you have all of this truncated. I am talking about numerical purpose, how we can have this numerically. Closed form, we don't know. I don't know whether anybody can find closed form, even for finite dimension. So maybe we use a generating function or Z transformation, it's called. And we use norming for purpose of norming, actually, norming probability 1. And also this generating function has a good idea that you can also find expectation as well. And it's easier when the bound up the first row of my example is all the same as the second row. In this case, this is much easier calculation. Now, this is probability, this is generating function. We have always problem to find numerically the inverse of a matrix. But for mathematicians, it is not really any problem. We just use inverse. But numerically is important to find the inverse of a matrix in terms of complexity. Now, what we do, first, we find an approximation for pi I, call it pi I tilde. And for initial set one of them to be 1. And then you end up with that. And then actual probability is going to be this approximation divided by C to make sure that the sum is 1. Also, there is another method that we can use by so-called generalized eigenvalues. So generalized eigenvalues actually was used before matrix-analytic method, historically. And is based on generating function. Everybody knows that. And both methods are close to ECM with repeat rows, of course. And characteristic roots are replaced by generalized eigenvalues. And what is generalized eigenvalue? This is number 5. Lambda is generalized eigenvalue, and mu is, or V is generalized eigenvector. So we end up with pi 0 by this sigma, and then pi j for j less than h, and pi j bigger than h, and first replace the pi I in the above equation by just general solution, mu xi, as every differential equation can be solved like that, or difference equation, or whatever you call it. And then you end up with a vector and a scalar. Satisfy that. This can be converted into a generalized eigenvalue problem and solve such as such. Now, what I am saying here then, if the size of matrices block are finite, no problem. This is pi j. Sigma finite, you have everything. However, if the size of matrices are not finite, infinite, then you end up with summation, infinite summation. You may use truncation for this summation or approximation, like Taylor series. And now I am going to give you one example. Everybody knows shorter Q, of course. Shorter Q can be infinite and infinite, both variable, but you can convert it into infinite and finite. As X1 is longer line and L2 shorter line, and then you look at X2 to be the difference between shorter and longer. So actual random variable is X1 and X2. So X1 is infinite, X2 is finite, always. So shorter Q can convert into the finite case. Now, tandem Q with no block. So meaning that you have two stationary, two server, and between them is infinite. There is no block. Two lines, both unbounded. So then in this case, we use eigensolution. And we end up with this if it is finite. But then we have infinite. This is no problem. This is no problem. But if N change into infinite, there is a problem. We don't know what to do. And that's all I want to say today.